There's our folder for the week. Up at the top, you can see you got another folder for the extra practice. That worksheet up at the top, I'm going to give you a hard copy of that. And then there's the answer key to that worksheet in here. So if you're looking at the Paul's Online Notes packet and saying, you know what, this is a bit overkill, this is too hard, let's look at something that's more manageable, maybe that'll be better review for your quiz on Wednesday. Then if you're like, you know, I like a challenge and I like suffering, here are answer keys to more problems from the Paul's Online Notes packet. If you want more video help, these are all, do you guys know about the Organic Chemistry Tutor? Yeah, he's great. He makes good videos. He's almost as good as me. The advantage is his videos are already done, so I'm just going to plagiarize them. If you want practice with videos, there's just a whole bunch of different kind of problems. You have an airplane problem, which is probably good to look at. You got different shadow problems. You got angle elevation problems. You got cone, sphere, cube, any kind of problem you want on related rates. It's in there. And then each of these videos probably has anywhere from like 2 to 4 problems within the video. You don't need to watch the whole video. Just kind of poke around within a video, kind of jump ahead and see what you have. And if you see a video it's like, oh, actually, that looks pretty helpful. That looks like something that we did that I could review. Then you just watch that snippet of the video is maybe worth your time. Yes? No, never mind. Okay. So you got a whole bunch of videos from Mr. Chemistry Tutor from YouTube there. And then tomorrow I'm going to be out, which is no great loss because it's fake school tomorrow anyway, because virtual is crap. So tomorrow your job is to just keep preparing for tomorrow's quiz, Wednesday's quiz. And you've just got Paul's Online Notes packet, you got your textbook, you got this extra worksheet that I'm going to give you, you got those videos that I linked there in that yellow folder up at the top of the week. You can get together in the Google Meet tomorrow because somebody's going to cover this class for me tomorrow, and they'll open up the Google Meet, and you get in there, and you talk to each other, and don't be shy, or go ahead and be shy, I don't care. And that can maybe help you prepare for Wednesday. And if you haven't yet, would you please do, where is it? The survey. Where'd the survey go? I'll put the survey in here later. So the survey where you get to grade me and tell me how wonderful I am, I'll have that in here at the top of the week. Please do that also if you haven't done it yet. If you have done it yet, you're also wonderful. Thank you. Any questions? Nah, cool. All right. Go away. And Lucas, you know what? Let's just leave the light off. It's already muggy and hot. We don't need more light. Is there anything that you want to look at from the Paul's Online Notes set of problems that I've assigned for officially being due Wednesday that I gave you guys time on Friday to look at? Yes, Olivia. Which one? 20. Yeah, let's look at 20. We might not work all the way through it, but I can kind of give you at least a jump start on it. So 20, you've got your cone, and it's leaking water, so here's your cone. Look at that cone. Have you ever seen such a beautiful cone? All right, so it's leaking water, drip, 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 drip. And then you've got the height of the entire cone is what? 2.5 meters. That's for the cone itself. You've got the radius for the entire cone. And that's what? 1? Yeah. That's for the entire cone. And then we've got water inside the cone. We'll call that green water, I guess. That's what I have here. So the water inside the cone is only like halfway up. So that's the height of the water, is what, 1.25? And water is leaking out at a rate of negative 35 cubic centimeters per second. What would be a label for this? just V dV dt. So why is it dV dt and not just plain old V? Because it's changing over time. Yeah, you see the units, it's not just centimeters cubed, it's centimeters cubed per second. So that tells you it's a rate of change. And if you read the problem, it says, is leaking water at a rate of 35 cubic centimeters. Why did I make it negative? Because it's leaking. So water is draining out, so the water level is going down. So what we want to do in part A is find out at what rate is the depth of the water changing, which I'm calling height. So what's dH dt? And then in part B, what's the rate of change of the radius of the top of the water? So you have a height for the whole cone, but then you also have a height for just the water. So the height of the whole cone is fixed. The cone itself isn't changing shape or size, but the water within the cone is changing, and that's what we want to key in on. This stuff about the whole cone just gives us like a relationship between the radius and height that we can then use for the radius and height of the water so that we can substitute and get rid of R in our volume equation. Speaking of our volume equation, we should probably have that written down 1/3 pi r squared h. So that's kind of set up there. Any questions with just kind of big scenario, labeling stuff, general information? Because at this point, we've just kind of taken information, written it down. We haven't done any math yet, really. Yes, I am recording this. It's almost even visible on the screen. So we're cool with just setup. So what's tough about this is how do we use the dimensions of the big cone to help us out? What we want to do is use those dimensions to try to eliminate the radius variable from our volume equation. So let's create a proportion. So what is the radius of the entire cone? 1. And what's the height of the entire cone? 2.5. And guess what? Fraction that. And now you've got a proportion. So now we have this relationship. Oh my goodness, it's disgusting in here. Now you've got this relationship between the radius and the height, and a cone that's kind of embedded within a larger cone, they're going to be similar shapes. So they're going to have the same ratio of radius to height. So the cone for the water is going to have the same ratio of radius to height as the cone of the entire tank does. So what we can do is say, well, we want to talk about the height and how that's changing in part A. So let's get our volume equation totally in terms of height and hide the radius variable. So to do that, we'll isolate our R, and then we'll have something to substitute into the volume equation for R. So to isolate the R, what do we do with the H here? We multiply it over. So multiply both sides by H. That dies. You have R equals 1 over 2.5H. And now you can take that and plug it into your volume formula for the cone of water. So this is the volume of the water that we really care about. Say, hey, I know what radius is, sort of. I know it's 1 over 2.5 times H. And that allows me to have this volume formula totally in terms of H. And now I only have one variable, and that's a plus. I lost an H there. So this is the volume of the water. And as the volume changes, so is the height changing. So I'm leaking out water, and as a result, the height of the water level goes down. And so now I can kind of start to clean this thing up and do your derivative. So that's kind of the key trick, if you want to call it a trick. That substitution using the dimensions of the big cone to create a proportion of radius to height that you can then use to substitute for radius in your volume equation and eliminate your R variable. And then when you square this, how many H's do you really have running around up top? 3, right? Because you have an H squared and another H, so that's H cubed. And then in your denominator, you have 2.5 squared times another 3. So what's 2.5 squared times 3? So 6.25 times 3 is 18.75. So you can square the whole fraction here. 2.5 squared gives you 6.25 times the 3 that's already down there. Now you have a new denominator. So you have a pi, you have an h squared, and another h, make h cubed, and then that's all over 18.75. That's going to be the volume formula that we now use and differentiate. So go ahead and differentiate that. What do you get? dV over dt is a good start. And over here, you're just doing power rule. So 3 pi h squared over 18.75 times dh dt. So you did the derivative of an h thing with respect to time, slap a dh dt on that. And now you're ready to plug everything in that you know and solve for dh dt. You're ready to finish off part A, basically, because you know dV dt, that's the rate at which we're leaking water. So that's negative 35. You know 3 pi, because, you know, they're numbers. You know h, that was told you, that's the height of the water, the depth of the water, same thing, so that's 1.25 squared. And it's over 18.75. So you plug all your numbers in that you have for dV dt and for h, and you can find out what dH dt is. If I were me, I usually am me, if I were me, I would just take this big nasty fraction and just like multiply it out and make it a decimal. And then just divide the decimal over. Yes. Oh, wait.
Meters.
The meter. Oh, I totally forgot that again. All right, so yeah, what's the height being measured in? Meters. What's the volume being measured in? Centimeters cubed. These bastards. All right, so this is in meters, and that's in centimeters cubed. Thank you, Prince. That's definitely a board point. So you got to punch out for that, or they'll get you. So 1.25 meters is how many centimeters? 125? All right, so let's make this 125. Is that the only thing that needs to change? 18.7. I don't. Oh, you know what? Maybe.
Yes.
No, because the 18.75 just came out of the squaring the ratio. And the ratio doesn't care how, that's just kind of like scaling up or scaling down. The scaling issue isn't going to be a problem. But yeah, when you actually go to plug in a number for h, that needs to be on the same page units-wise as the units for v. So if your v is in centimeters cubed and your h is in meters, you got to turn your h into centimeters, because that's going to be a lot easier than turning this thing into meters cubed. So yeah, make that 125, not 1.25. Thank you, Prince. Sorry about that. So when you go ahead and do that, can somebody tell me what this fraction makes as a decimal? So 3 pi times 125 squared divided by 18.75. $6.25? The whole thing. So this whole fraction, there's no way that's 6.25. It's going to be way bigger than that. How am I going to say it's way bigger than 6.25, and then you lead up, well, maybe it's 0 point. What did you say, Zelda? 7,000? 7,853.98. I can buy it. That seems a lot more reasonable than 0 point whatever. Yeah, 125 squared is going to be big. Then multiply by 3 pi, and it's bigger. Then you divide by 18.75. It'll still be big. So divide by 7853.98. And what's negative 35 divided by that number? Now you get 0 point something. 4456. Let's call it 446. And the height was measured in centimeters because we changed it here. So that's going to be centimeters per second. All right, cool. Check the answer key. Yay, I agree with me. All right, cool. So that's our dH dt. Pause. Questions? No, that's evil. Paul is more evil than I am. So that's why I like him. He's a good guy, but I'm not going to do that to you. Why a good guy? I mean, an evil person. I'm not going to do that to you on a quiz. Now, dRdt, part B, we also want to know how is the radius of the top of the water changing? And you might think, oh my God, do I have to go all the way back to the beginning and do the same thing all over again, but swap out H instead of swapping out R? You could do it that way, but let's find a less painful way. You see this thing? Just differentiate that. And then you know what dHdt is, plug it in, and you got dRdt. So for part B, that is where you make your ratio relationship between the radius and the height do some more work for you. So let's look at that ratio relationship, 1 over 2.5h. If you just differentiate that, what do you get? dRdt is a good start, equals divided by, or the way I have it written there, 1 over 2.5 is like a coefficient times dHdt. Now, if you don't like fractions, you could multiply the 2.5 up and over here, and then you'd have 2.5 dRdt equals dHdt, same thing. And once you've got that, you're like, oh, I'm looking for dRdt, that's the goal in part B. I have dHdt, I just found that about 4.7 seconds ago, so, and see what you get. So, what's that number divided by another 2.5? 1782. All right. And again, that's in centimeters per second.
Wait, isn't it?
It doesn't matter because that's just a ratio. So you see when you set this up, that was in meters and that was in meters. So what would happen to the units? They die. So it's just a fraction with no units attached to it anymore. The units would cancel out. So the ratio equation has no units kind of built in. You can use whatever units you want. So if the radius is 3 feet, then this is 1 over 2.5 times h, and that's h in feet. We could now switch to any units you want. It won't make a difference. So then that's done. So like all the heavy lifting is, in my mind, in part A. In part B, if you just see, oh, just use this ratio relationship equation and differentiate that, then part B is not a whole lot of work. But the creativity here comes from using the dimensions to get this relationship between radius and height so that you can substitute into your volume formula and get rid of your R equation before you differentiate. Follow up on that? An analogous question on the quiz will be easier in that instead of just saying, here are the dimensions, figure out the relationship, instead it'll be something along the lines of, the height is 3 times the radius. And then you'll just have explicitly in words that h equals the 3 times the radius, and you won't have to kind of build that for yourself. You'll just have to read, the height is 3 times the radius, and say, oh, then h equals 3r, and that's what I'm substituting, or something like that. So it won't be kind of this next level, take the dimensions of this large shape and use those to kind of build the relationship yourself. Follow up with that? Anything else we want to look at from the packet? Yes. 25. Is 25 a one-word answer? Assuming that the elevator, like, you mean yes or no?
Well, like, is it increasing
Oh, yes. I should have given you guys 24. 25 is a lot harder than 24. Sorry. I do have an answer key for 24 on one of the other things in that folder that I showed you guys. So 25, you've got the picture there. At least they gave you a picture. That's nice of them. And this is good because it's an angle problem. And you'll have one of those, not to this degree of difficulty, on your quiz. So you've got you, and you've got, where's the elevator? Up high? And then the elevator is coming down. And you are walking towards the elevator. The elevator's going up. So you're chasing the elevator, and then it went up. 25, right? All right, so elevator's going up. Sorry. I got left and right confused. It's its own kind of entertainment, I guess. So we have the height of the elevator. Is the height changing? Yeah, because it's going up. So that's going to be a variable. We have the distance from you to the elevator doors. We'll call that x. Is that changing? Yeah, because you're running. It's like, no, hold the door for me. And they're like, no, screw you, we're going. And then you've got the angle, you looking up at the elevator. No! All right, so then you have the angle of elevation of you looking up the elevator as it goes up. I guess it's one of these nice glass ones that you maybe see at fancy places. They can look down at you and laugh. So originally, what's x? 24. Do we know the current height of the elevator? No. We have, where does the elevator begin? I guess this is after 10 seconds. This is another one of those problems that here's all the rates, and 10 seconds later, so the elevator started at the ground and then goes up at a rate. So h equals 0 because it starts on the ground, but then it's going up at what rate? 4 feet per second. So 0 plus 4 feet per second times the number of seconds. And we're doing this at 10 seconds. So how high is the elevator right now? Like at this moment in time? 40 feet? So h equals 40 feet right now, 10 seconds into this whole scenario, which is where we care about. So we care about when time equals 10. And then I guess the 24 feet is where the person starts, but then they're moving at what rate? 0.75 feet per second? Yeah. So the person's moving at a rate of 0.75 feet per second. So after 10 seconds, and why did I make this a negative 0.75? Yeah, because you're running towards the elevator doors, so this distance from you to the doors is getting smaller. So x is getting smaller as you run, and 0.75 feet per second is not a very urgent run, I guess. It's very slow and meandering. So after 10 seconds, what's 24 minus 0.75 times 10? 16.5? So actually 16.5 feet is how far you are right now. We care about at 10 seconds. So you start 24 feet away, and the elevator starts on the ground. And then I'm on the stopwatch, and I say, go. And you start running slowly towards the elevator at 0.75 feet per second. The elevator starts going up. And 10 seconds later, I say, stop. What's the rate of change of the angle? Makes sense, right? Because obviously this is what you do at the mall. You go window shopping, you're like, anyway. All right, so this is at t equals 10 seconds. When we care. So the goal here, I believe, is the rate of change of the angle, d theta dt. So what trig function, you know it's a trig function because you're talking about an angle. What trig function are we going to need to use here? Tangent, right? Because you do opposite over adjacent, opposite over adjacent. So we're using tangent. So tangent of theta is the height over the ground distance. And all three of these are variables, right? The theta is a variable because that's changing as you and the elevator move. The height is changing because the elevator is going up. And the ground distance is changing because you're running after the elevator. So everything here is changing. Everything's a variable. Oh boy. The good news is we know h right now. We know x right now. We know dh dt. Because what's dh dt? 4, because that's the speed of the elevator. So let's give it a name. That's dh dt. We know dx dt. That's how fast you're running. So what's dx dt? 0.75, and it is negative because that's making x smaller. dh dt is positive because that's making h bigger because it's going up. So all you need to find out, all you need to find out is what's theta right now, and then you can take the derivative and find out d theta dt. So to find out theta right now, go ahead and plug in your current h and your current x into this equation. So you have tangent of theta equals 40 over 16.5, and you do your whole inverse tangent business with your calculator, and what do you get for the angle right now? $67.5. I'm going to go out on a limb and say you're in degrees. And you're probably in radians. It doesn't really matter which you do, but I'm going to go into radians. So 1.18 radians. Does anybody have a different radian number besides 1.18? Yeah? Okay. So that's your angle right now. And now, guess what you do with your tangent equation? You're going to differentiate it. So when in doubt, differentiate your main equation. In this case, your main equation has to deal with the angle, because that's what we care about. So when you differentiate, what's the derivative of tangent? Secant squared theta. So we got secant squared theta times not yet d theta dt. So you got to have a d theta dt because that's what we want to know about. And then over here, what do we have to do with h over x? Quotient rule, because it's a quotient of two variables. Like both of these is a variable, you have to do your quotient rule. So low d high, low is x, d high is dh dt, minus high d low, high is h, d low is dx dt, and low is x squared. So plug in all your numbers over here. Current x is 16.5. dh dt is the speed of the elevator, 4, minus current h is 40. dx dt is the speed of u, negative 0.75. X squared is the current x, here's that again, 16.5 squared. And theta, first of all, do you like secant? No. To get it over to the other side, what can it turn into? Not inverse, reciprocal, cosine, I know what you mean. So cosine, so instead of dividing by secant squared, multiply by its reciprocal to the other side, and you get cosine squared. And what's the current angle? Oh, it's 1.18. 1.18 over here. So you have multiply the secant over to the other side. That makes it cosine of 1.18 all squared, and then times your quotient rule fraction. Yes, Prince.
So will you want the arrow? Yeah, and then the denominator. Yeah, right. Yeah, how much is x times
So I'm doing quotient rule, right, on this fraction? Because it's a fraction, and they're both variables. If the denominator was like 5, I could just say, oh, it's dh dt over 5. But because the top and the bottom are both variables, I have to do quotient rule. And so that's where this comes from. Any other questions with that? Yeah, Akshay? I divided both sides by secant squared, but then I don't like secant squared. So dividing is the same as multiplying by the reciprocal, and the reciprocal of secant is cosine. So instead of dividing by secant, I'm now multiplying by its reciprocal, which is cosine. You could think of this as like 1 over cosine squared, and then I multiply the cosine over here. Maybe that's the Any other comments or questions with this? So now, at this point, it's can you push buttons on the calculator? Which is an open question. This is not like the easiest button pushing problem at this point. So for cosine squared of 1.18, what I would do is cosine of 1.18, and then see what I get and square that. So when I do that, what's cosine of 1.18 squared? 0.1451 is what you said? All right. Then in here, what's 16.5 times 4 minus 40 times negative 0.75? That's 96. Oh, that's nice. And on the bottom, what's 16.5 all squared? 200 and 272.25. Okay, I can buy that. And then times 0.1451 with 96 and divide by 272.25. And what do we get? I'm guessing it's a 0 point number. 0.512. 0.0512. All right, let's move the decimal. 0.0512. Our units for the angle of the rate of change of the angle always is going to be in radians per time. So even if I went with Iman's original number of 67 degrees and change, this will be still 0.0512 radians per second. Because once you've done the cosine of that angle, now this is just a number with no units attached to it. And over here, all the units will wash out. So this is just going to be radians per whatever second. Now the question was, is the angle of elevation increasing or decreasing? So look at that. Is the angle of elevation increasing or decreasing at this time? Because positive, yeah. So you look at that, oh, it's positive, so the angle must be increasing. So I guess that means the elevator is going up in such a way that you running at it, actually, as you run at it, we probably could have solved that without doing any math at all. Yeah, you could have answered increasing and done zero math if you just thought a little bit. Oops, Raisa, talk to us. How could we have done this without doing any of this math? The answer increasing. Well, it'll still be increasing. Yeah. It'll still be increasing. Yeah, it's going to be increasing. Because so what she said about the elevator being stationary, what we should do here, instead of doing all this math, is just do two thought experiments. What if I stand still and the elevator goes up? What happens with the angle? It increases. Now, a little bit more difficult to think about. What if the elevator stands still and I walk towards it? So, see that TV? That's the elevator. If I walk towards it and I keep my eyes on the elevator, what happens with my eyes? I have to tilt my head back, so what's happening in the angle? It's increasing. So, if I stand still and the elevator moves up, the angle goes up. If I move forward and the elevator stands still, the angle goes up. So since each of those on their own would mean, well, the angle's going up, put them together and the angle is going to go upper, right?
You wouldn't accept that as an answer.
I would absolutely accept that as an
Oh,
answer.
you would?
Yeah, because if you read the problem, that's where reading helps. The question was not, what is the rate of change of the angle of elevation? If that were the question, then I would want all this, because then I would want that number. But if the question is it increasing or decreasing, that angle? Then, totally fine to give you that thought experiment way of doing things. Hell of a lot more clever and quicker. Well, yeah. Kind of like with the way we just did with, like, hey, if this stays put and this goes up, the angle's going to go up, and vice versa. So, but yeah. On a quiz, like maybe Wednesday when you have one, I will want the number. But this is a good problem. Again, the problem on the quiz is not as hard as this one. What makes this one especially difficult is all this business about 10 seconds after we start. It's like, well, how about we just tell you about right now? I'll do that. All right, so I'm going to tell you what are things right now, and I'm not going to worry about like basically having a separate function for h and for x. That complicates things even further. Wow, these are long. All right, that's 5 minutes left. Anything else? Maybe a. No, just those two. So 1 through, what was it? How are 1 and 2? Other than like super tedious, but being able to do them. 1 and 2. I can't remember.
Yeah, and then we got like 8 different answers.
Oh yeah, that's right. Yeah, 2 is. Yeah, but that comes from tediousness and like forgetting. Oh right, that's product rule. The one on the quiz that deals with stuff like number 1 and 2, that's just generic x, y, is a lot easier than 1 and 2. Then 5 through 9 are good problems. You'll have one problem similar to stuff with 5 through 9 with like these just geometric formula problems. In tomorrow's folder, I have the types of problems that you will have on the quiz. So I'm telling you what's on the quiz for Wednesday. It's there in tomorrow's folder in terms of like, you should be ready for this kind of problem, and this kind of problem, and this kind of problem. And it was 5 problems in 43 minutes plus a bonus.
Okay. Is the homework tomorrow or maybe it's Wednesday?
I'll take it Wednesday. Yeah, tomorrow is a chance for you guys to talk to each other in the Google Meet, which you may or may not do. I won't be there. It's up to you. And kind of share ideas on how to attack some of these. Or you can look at other stuff besides the official homework, and maybe that'll be more beneficial.
Okay. Wow.
Yeah. Swell?
Wow.
That sounds swell to me. Okay. All right, I got to take attendance.